Morning, everyone. Yeah, to my class.
Morning.
Morning. Thanks for the questions, Daniel.
Oh, hey. No problem. I went out of my mind yesterday trying to figure them
out. Okay, let me see. Do you guys see the PowerPoint right now?
No, I see you.
Okay, bummer. Hold on. How do I want to do this today? I'll try that. There's that.
Yep, I see the PowerPoint.
Okay, yeah, in a little bit I'll bring the whiteboard up. Let people in.
How are you?
I'm good. I'm back in San Diego. How are you?
I'm okay.
That doesn't sound enthusiastic.
Nah, things are all right.
It's tough. It's you know, it's bizarre. Right?
Yeah. The weather's great though.
It was really good in New Mexico. The evenings were really pretty. Although they have a moth infestation because it's dry, and I read that the moths are coming down from the mountains to get water, and so at sunset there would just be all these moths would come out, and every time I moved something in the yard it would free up a bunch of moths. I opened up a door into another building, and all these moths came out.
Oh wow.
Yeah, they were everywhere. Okay, let me close that. And the second question you asked, I don't know, was the longer one. A lot of people miss that on the homework, so it'll be a good one to do.
Okay.
Let me get my calculator. Oh. Did you look at the IMF stuff yet? Intermolecular forces?
Yeah, I did. I started reading.
What do you think about it?
I only did about a third of the chapter. Okay. It seemed pretty straightforward.
Yeah, the first part of the chapter is review, and some of that stuff in the other flavor of this class, I cover early on. When we do energy and matter, I cover a lot of that stuff then when I do Chem 100. And I think if I teach 152 again, I'm going to move that part of it back there. I think it makes more sense to cover it then.
Right.
But I'll say some things about intermolecular forces that pretty much summarize what's there, but I think it's always helpful to hear it in addition to seeing it.
Yeah, definitely.
Okay. Well, hopefully it's helpful. What time is it? So we're at 9:32. Let me just see if I've got more people coming in. Okay. I think I'm good for now. So I'll start with this, and then I'll start with the questions because I think they'll be helpful. And then as people come in, as people chime, I'll let them in. Okay, so happy Monday. Last chapter, last exam, big week. So so I thought today I'll answer a couple questions that got sent in about equilibrium. Whoa. I think this happened the last lecture. I've got something asking me if I want recipes. So last chapter, I'll answer some questions about equilibrium. I'll say a few things about intermolecular forces. The slides are here. Some of it in the beginning is review. Skip these slides here that have more quantitative questions that I won't cover at this point in the semester. So Wednesday is exam 4, our last midterm. Please email me questions ahead of time. I'm not planning to Zoom before the exam, but if people want last minute questions, I can do it, but can we do it earlier so that I can get on with the day? Because I got some other stuff I got to take care of. Would it be possible to do, well, just, I guess, email me. 7:30 or 8 is better than 9:30 if we have questions, because then I can start the exam when it's supposed to start, which would be 9:30. And it'll be the exam will be the same format as last time. It'll be all on Canvas. And it seemed administratively that worked pretty well. And so I'm just gonna, it is gonna be more like that. There's 31 multiple choice, and I'm thinking about 2 questions per chapter, roughly. Any questions on that stuff?
Yeah, I have one question, Professor.
Uh-huh.
When does the exam due? I mean, we started, but like Saturday at noon or?
Oh, well, we can do it the same as last time. We can do Saturday at noon. Let me write that down.
I don't know. I forgot how you did it the last time, what day it was due.
I think it was Saturday. Well, last time I extended it because I wanted you to do the lab before the exam because I thought the lab was going to help. I'd kind of like to get it done early, but there's not really a compelling reason because it's just a review and we have the weekend. So I think what I'll do is I'm going to write this down now for a note for myself. 2-hour window. And it will be due Saturday morning at 11 a.m.
And it's available on Wednesday?
Yeah, starting at class time on Wednesday.
Okay. And do we get to make a little card?
Yeah, card is fine.
Okay.
Let me write this down. Actually, I might as well put it here, right? So exam, 2-hour window, beginning 9:30 a.m. Wednesday, due Saturday, 11 a.m. Note card. Okay. What other details do we have? Well, it'll be the same thing where you complete your answers in Canvas and then you upload in Canvas quiz in the 2-hour window, and then upload your work afterwards.
And how much time do we have to upload after the 2 hours?
Oh, I didn't put a limit on it, but I would note, like, if it were a long time after, like 12 hours after, it would give me a flag.
Okay.
Yeah. So, I mean, the answer is like, as long as it takes you, but don't like go have lunch and come back and upload your file.
Okay. Understood.
Yeah, thank you. After you are done. Okay. Okay, so let's go over, there were a couple questions on equilibrium. I'm gonna change my screen share, look at those. Okay. Okay, oh, I'm a little slow, huh? So there was a question on the homework about KSP, and KSPs are an equilibrium constant. That's it's a name that refers to something dissolving. And so if you have an ionic compound MX, where M is the cation and X is the anion, its dissolving into an aqueous solution can be represented in an equilibrium like that. And the question that I got was, if the concentration at equilibrium of M plus is equal to 3.1 times 10 to the minus 3 molar, what is the value of the KSP? And what we know is that when MX dissolves, each MX that dissolves makes one M plus cation and one X minus anion. So if this is 3.1 times 10 to the minus 3 molar, X minus is also going to be 10 to the minus 3 molar. And this equilibrium expression, because mx is a solid, we don't include that in the equilibrium constant, because we only include aqueous and gases in our equilibrium constant. So the equilibrium constant will be calculated on the concentration of M plus times the concentration of X minus. And so that would be 3.1 times 10 to the minus 3 molar times 3.1 times 10 to the minus 3 molar, or just the square of that. And that number would be, let's see, 3.1. I get 9.6 times 10 to the minus 6. So I think that, and the equilibrium constant is generally without unit. So the, yeah,
If solids are not, don't get used, liquids, water doesn't get used.
correct.
Liquids don't get used also, correct?
Correct. Yeah. So
Okay.
aqueous and gases.
Now, Professor, on the exam, if you give us an equation like that, are you going to tell us if it's a solid or it's aqueous, or do we have to figure that out for ourselves?
Well, if this is a KSP, it's a solid dissolving into aqueous solution.
That's a given. Okay.
Yeah, that's a good point.
So, Professor, can you explain how you know the anion has the same molarity as the cation?
If we make the assumption that all of it came from this getting dissolved, then they have to be the same, right? Every time an MX splits up, you get an M plus and an X minus.
Right.
But you're right. You know, you could, like, let's say this is Cl minus, the X minus. If I threw some, and maybe this was calcium, well, that wouldn't work. Let's say this was KCl, right? My M plus would be K plus.
It's weird.
Right.
If I threw some sodium chloride, oops, I'm off screen. If I threw some sodium chloride into the solution, that would make Na plus and Cl minus. So it would bump up this concentration, but not that one.
Right.
So it is possible, I think, yeah, it would be possible to have different concentrations if I introduce it from a different source.
Okay.
So I have to look at how it was worded in the homework. Because that's a fair question. But if you are starting with just that salt, it's going to be 1-to-1.
Is that true for every salt?
Well, so let me go get a paper towel. Hold on a sec to wipe my board. So it's going to be in the ratio of what you dissolve. So if I had, and that's also a good question, if I had magnesium chloride, well, actually, that's going to be really soluble, but let me pick something that would be not as soluble. If I had that, right? Magnesium hydroxide, that will split up into Mg 2 plus 2 OH minus. So if we were given a concentration of this is too high, but 0.2 molar of magnesium, we would know that the concentration of the hydroxide is 0.4 molar because of the 2.
I see.
Yeah.
Okay.
And that's generally how these are going to be approached. The kinds of questions you're going to see. You're going to make the assumption that it's all coming from this.
So the coefficients determine the ratio.
Yes. Yeah.
Okay. All right. Thank you. Appreciate it.
Oh, yeah. Good question. Okay. Then, yeah.
This type of problem, that KSP, so if you had 2 reactants, it would be the 2 products over the 2 reactants, correct? And that's one of them was a solid. Say you had this MgOH2 plus something going to the 2 reactants over there.
2 products.
2 products, and you have going to 2 reactants.
Oh. If I had.
So that would be the 2 reactants divided by the 2 products, correct?
Yes. As long as they're all aqueous or gas.
Aqueous or gas. So one was a solid, it would not be there, or one was the liquid, right?
Right.
And if that, you have the X minus there, and you have the Cl above it, say that Cl would have been, like 2 moles, that would have been squared, wouldn't it? It would have been the M.
That.
But,
yes.
okay.
Right. So yeah, actually, so if I have magnesium hydroxide and it's in equilibrium with magnesium 2 plus and 2 hydroxide, this is solid, this is aqueous, that's aqueous. My equilibrium expression would be, in this case, because that's a solid, it would be magnesium concentration, not moles, concentration, moles over liters, times the hydroxide concentration squared.
Yes. Okay.
Yeah. Okay, so a question that a lot of people missed on the homework had to do with an equilibrium in the gas state. And I kind of like this problem because it brings up, it's actually a good final exam kind of question because it brings up things from 2 different chapters. So let's go over that one. So this is carbon monoxide gas plus Cl2 gas is in equilibrium with, I don't even know how to call that, what the name of that is, that gas, COCl2. You are given that the equilibrium constant is 6.17 times 10 to the minus 2. And you're also given that at equilibrium, the concentration of carbon monoxide is 0.285 molar. And the concentration of, and you'll have different numbers with your individual homeworks, 0.0120 molar. And the question is, what is the mass of the product gas at equilibrium? So what we can do is we can use the equilibrium constant to give us the molarity of COCl2. And we're also told that the volume of the gas is 5.89 liters. And I think the temperature was 25 degrees Celsius. So let's see. I don't know if I guess we need that to get, we need that to get the moles. Okay, so the equilibrium constant is going to be equal to the concentration of COCl2 times the concentration of CO times the concentration of Cl2. And we've been given those two. And we have this, so we can get out that. So 6.17 times 10 to the minus 2 is equal to x divided by 0.285 molar times 0.0120 molar of the chlorine gas. So x will be this times those two things. And let's see, you guys can see, well, I'll just do it. 6.17 times 10 to the negative 2 times 0.285 times 0.012. And I get x, my concentration of the COCl2 gas is 2.11 times 10 to the minus 4. And that's molar. And remember, molarity is moles over liters. So 2.11 times 10 to the minus 4 moles over liters times the volume is 5.89 liters. That gives me the number of moles. And so that would be 1.24 times 10 to the minus 3 moles. And then I'm going to use the molar mass to get the number of grams. Let me see. 1.24 times 10 to the minus 3 moles times the number of grams per mole. And that's going to be 12. I don't know if I have a periodic table nearby. 12.01 plus 16. And then chlorine's 35.45. 35.45 times 2. So I get 98.9 for the molar mass. And so I get, my answer is 0.123 grams of the gas. So that was a lot of talking. So do you guys follow what I did?
Mm-hmm.
Yes.
Okay, yeah. So the first thing is to get this in moles per liter, and then use the volume to get the number of moles, and then the molar mass.
Another question, Professor.
Uh-huh.
Say you have two products up here, like you got the CO and the Cl2, but you know it's a little bit more complicated.
Uh-huh.
Would we have to know what products were generated from what reactants, or you give us an equation similar to what you just did up here with the CO gas, Cl2 gas, when the CO. Sometimes I get confused on what reactants are being formed from what.
What product?
What products are being formed from what reactants? They get pretty complicated.
Well,
I got caught up on it bad.
oh no. Well, so I think it's fair to put into writing what the reactants are and what the products are. But
Okay.
my goal here is to figure out what you know about equilibrium. So I would rather give you the equation so that I can actually see that part of what you're understanding. You know what I mean? So that's how I would approach it. And also it allows me to test more things on equilibrium if I make this part more straightforward. You know what I mean? Because I want to ask if you know this, and then if you can do that afterwards. So I would, it could happen, but my preference is to do this, is to give it to you.
Okay. Because I can't get the first part. You might as well try to get the rest of it.
Right, and then I don't get to see what you know.
Yeah.
Right? So that's what I would.
Times you had two products, then it goes to three reactants, and that's where I really get confused.
Ooh, well, that's a lot of work. Okay, so I'm gonna erase this, and I think I want to just say some things about intermolecular forces. Okay, so maybe I'll just do it here. Okay, so one thing, we're talking about intermolecular forces in this chapter. And one of the first hurdles is people forget what that means. So here's a water molecule, right? What kind of bond is that? Is it an ionic bond or a covalent bond?
Covalent.
This is covalent, right? This is polar covalent.
Right.
Okay, so remember that is intramolecular.
Right.
That's not what this chapter is talking about. Those are strong. What we're talking about is so I have one molecule here and I have another molecule here, and it turns out the molecules interact with each other. And so there are attractive forces between the molecules. Those attractive forces are intermolecular. And that's what this is focusing on. So it's between molecules, and these are weaker than intramolecular. And those are often, they're called IMFs. They're really important in biochemistry. They're important in a lot of things. And one way to remember that this is weak is to think about what happens during a phase change, right? If you have a pot of water, right, and you put a flame on it, you have water in here. When you reach the boiling point, water molecules leave the water and they turn into steam. So what happens when water boils, this is still H2O. This is H2O in here. When water boils, what gets broken up is this thing here. The intermolecular forces are lost because there's enough kinetic energy from the heat to separate the water molecules into the gas phase. There's enough thermal and kinetic energy that they leave the water, but it's still water. So the intramolecular bonds are unchanged, but we've lost the interactions between the molecules when it enters the gas phase. And because the heat was enough to break this, but not that, that's a reminder that the intramolecular bonds are much stronger than the intermolecular interactions. Okay, oh, we got somebody waiting. Let me admit him. Okay, so that's my pitch for just reminding you of what this is. And then the other thing is it's all about charges. Let me move this back so I have a little bit more space to work. Right? So much in chemistry can be explained with the fact that charges attract and opposite charges attract. And the bigger the charge, the stronger the attraction. So among the intermolecular forces, they range in how strong they are from the strongest to the weakest. Oops, let me see if I can get this on screen here. Okay, strongest to weakest. And for the most part, the bigger the charge, the stronger the interaction. And the other thing is, the stronger the IMF, that's going to give higher boiling points. So think about the boiling point is indicative of how much energy, how much heat it takes for molecules to separate from each other. So the more heat, the stronger the interaction between the molecules. And the strongest intermolecular force would be called the ion pair, the interactions that are in a salt crystal. And for that, an example would be Na plus and Cl minus. We have a full +1 charge and a full -1 charge. And the interaction between those two ions is worth about 90 kilojoules per mole. It's the positive and minus charges attracting. But we also have interactions between ions and dipoles, and those are called ion-dipole interactions. And an example of that would be maybe a chloride anion being solubilized in water. So we know that water is polar, and there are partial positive charges on the hydrogen and partial negative charges on the oxygen. And so in water, and it's also, I want to point out that IMFs are usually indicated with dotted lines. Covalent bonds are represented with solid lines. So in water, the chloride anion is going to interact with the partial positive charge from water. And it's that interaction that allows sodium chloride, the chloride anions in sodium chloride, to dissolve. Because the number of those kind of interactions there's a lot of them per chloride anion. And that makes it more favorable for it to be surrounded by water than it is for it to be paired with the Na plus. Okay, so that question, yeah?
Aren't those called hydrogen bonds?
No, we're going to talk about, and I'll show you what a hydrogen bond is. And actually, where's my notes? That is the next strongest interaction.
So those bonds right here between that chloride and the hydrogen, those are called ion dipole bonds. They're not hydrogen bonds, correct?
Correct, because I have an ion, and then I have a dipole.
Okay.
Yeah, and so, if I've dissolved sodium chloride into solution, there's going to be similar interactions between the sodium and the water, and that would also be an ion dipole interaction. But now, because sodium is +1, it's going to interact with the negative part of the dipole in water. Right, opposites attract with electrostatic interactions, like that. And this is what you call solubilization. Hard to say, but it's the interactions between the water and the ion are so strong that it's strong enough that it separates them and they get dissolved in water. If the interactions between the ions in the water aren't favorable, or if the interactions between the two ions in their crystal solid are really strong, it won't dissolve. Okay, so this is the strongest IMF, although sometimes it's not referred to as an IMF, and I think your book doesn't mention it, but I like it because it shows what a full charge, a full positive and a full minus charge would be. And a step down from that is having a full negative charge and then a partial charge, right? Because this is just a dipole on the hydrogen, it's not a full +1. It's not as strong an interaction as this. Okay, and actually I'm going to skip down. The next one is the hydrogen bond, but it's a special kind of this one, which is called a dipole-dipole interaction. So I'm going to explain the dipole-dipole first. So a dipole-dipole interaction is between two dipoles. And one of the things that I don't love about the slides is that they show you molecular models. They show you red balls and white balls and black for carbon, but they don't show you the chemical formulas. And I think it's easy to lose what it is you're looking at because the formula isn't there. So in the dipole-dipole interaction, it's an interaction between two dipolar molecules. And so an example would be something like this. This is formaldehyde. So in this case, formaldehyde, each molecule has a dipole. That carbon is less electronegative than the oxygen, so it has a partial positive charge. The oxygen has a partial negative. And what happens is in solution, they tend to line up positive to negative. So here's a dipole, here's a dipole, and so it's called a dipole-dipole interaction. Still positive to negative, but because it's not a full positive charge and it's not a full negative charge, it's weaker than this 90 kilojoules per mole. The interaction for a regular dipole-dipole interaction is about 9 kilojoules per mole. So it's actually 1/10 the strength of the ion pair. Okay, now I didn't leave myself very much space to show you a hydrogen bond. Hydrogen bonds are between, it's a hydrogen that has to be attached to either an N, an O, or an F. So this hydrogen in water is attached to O, so it is able to hydrogen bond with other hydrogens that are attached to, well, actually with an N or an O or an F. So an example would be with ammonia. So that nitrogen in ammonia has that unbonded pair of electrons, and it has a partial negative. This has a partial positive. What makes this a hydrogen bond is this H is attached to an O. So water can hydrogen bond with itself. And there can be as many as 4 hydrogen bonds per water molecule. The hydrogen bond is stronger than the dipole-dipole on average, but weaker than the ion pair. Oops, let me fix this. So the hydrogen bond is about 20 kilojoules per mole. So stronger than dipole-dipole. It's actually considered a special case of dipole-dipole interaction because it's the dipole here on H and the dipole on the O. But on average, they are stronger than a regular dipole-dipole. And it's this hydrogen bonding in water that makes the boiling point so high. The boiling point of water is 100 degrees C. Molecules that don't have the ability to hydrogen bond with itself tend to have lower boiling points. So for example, this is formaldehyde. It can have a dipole-dipole interaction, but not a hydrogen bond. So we expect the boiling point of this to be lower than the water. Oh, so again, the hydrogen, you have to have hydrogens that are attached to N, O, or F. N and O are going to be by far the most common that you'll see, and those are what are really important in biochemistry. HF, because F can only bind to one thing, it's hydrogen fluoride, hydrofluoric acid. That's really the only case you see there. What's important to remember is that hydrogens attached to C cannot hydrogen bond. Those are nonpolar. Those do not have dipoles, does not hydrogen bond. And when you get into the middle of it, sometimes people forget that. Questions so far?
Ugh.
It's all in the PowerPoint slides, but I just wanted to give you my examples. And also there's a slide that summarizes all of this, except for the energies. Now there's one more type of intermolecular force, and that is the dispersion force. I'm gonna erase this so I have more space. So dispersion forces are sometimes also called London dispersion forces, or LDFs. And sometimes they're called van der Waals interactions. And this is between two nonpolar molecules. So there are no permanent dipoles. Right here in the ion pair, I have two full charges. In the ion dipole, I have a full charge and a partial charge. In the hydrogen bond, I have two partial charges interacting. In the dipole-dipole, I have two permanent dipoles that interact, right? Because I have something like this. With dispersion forces, the things you want to think about are hydrocarbons. It's between two nonpolar molecules. So imagine, move this down. Imagine you have propane. As soon as you see only carbons and hydrogens, you know that these first four things do not apply. So hydrocarbons have only dispersion forces. And these are the weakest because there's no permanent dipole. And so the example that would be similar in size to formaldehyde would be methane. Is methane a liquid or a gas at room temperature?
Methane.
It's natural gas. It's what comes out of your stove.
So
right?
it must be gas at room temperature.
Yeah, this is a gas at room temperature, which means the boiling point is really low. The boiling point for this is really low. It only has dispersion forces for the molecules to stick together. So if we remember that the hydrogen ion pairs have 90 kilojoules per mole of attraction, water molecules have about 20 kilojoules per mole. Dipoles are about 9 kilojoules per mole, right? 1/10 of an ion pair. Dispersion forces are 0.9 kilojoules per mole. So they're 1/100th of the strength of an ion pair. And so because of that, they're very weak interactions. Also know that all molecules have them. So even though the ion pair dispersion forces, my ion pair, my sodium chloride, it has an ion pair interaction, but it also has dispersion forces. However, the dispersion forces are 1% of the strength of the ion pair. They're there, but they're not significant. the vast majority of what keeps the ions together is the ion pair. And my water, when my water has hydrogen bonding, the water has dipole-dipole interactions, it has hydrogen bonding, and it has dispersion forces, because everything has dispersions. So if you are asked a question on an exam that says, what kind of intermolecular force does this molecule have? You always put dispersion force, because everything has dispersion forces. So in water, I would say it has hydrogen bonding, it has dipole-dipole, and it has dispersion forces. If you are asked what's the strongest interaction, you would say it's the hydrogen bond.
Professor?
Uh-huh.
Down here on this dispersion forces, all molecules have dispersion forces. So in
Yeah.
other words, it's not necessarily just two non-polar molecules. It could be two polar molecules there.
You're right. Yeah. Yes. You're right. So that's a good point. So it's the strongest interaction and the only interaction when you have two non-polar molecules. Yeah. Strongest for nonpolar. And the only one for nonpolar molecules. The other place where you're going to see them in this class a lot is going to be diatomics. So iodine, like I'll do that. Iodine is I2, right? This is a nonpolar bond, which means there's no dipole. So the only kind of interaction I2 can have is dispersion forces. And that would be true of any diatomic. N2, O2, Cl2, Br2, H2. Those only have dispersion forces. And those are all gases at room temperature, except maybe iodine, right? Iodine sublimates. But they're very weak interactions. Let me move this. Let me make sure I caught everything I wanted to cover. Oh, let me describe what dispersion forces are, because it's really odd. I honestly, I don't think I understood it until I was teaching general chemistry, what it really meant. So they say that they are instantaneous dipoles. And honestly, you don't have to fully understand what it is to be able to answer questions about it, but I think it's helpful. So they're instantaneous fluctuating dipoles. And they're so weak that the atomic radii need to be almost touching each other. So imagine I have my iodine and it's nonpolar. Oops. And it's close to another iodine. And imagine when it's by itself, there's no separation of charge. But when they're near each other, what happens is you get, actually I'll represent it as electrons. The electrons start moving together. Imagine my dots are electrons. You get sort of this temporary polarization of how the electrons are in the atoms. So if my electrons all move to the side of the iodine, this takes on the partial negative charge, this takes on a partial positive charge, and vice versa. And so now I have what's known as an instantaneous dipole that would go like this and like this. And so there's a positive and negative attraction between the neighboring molecules. But it's instantaneous. And what that means is that in the next moment, it can be reversed. So another snapshot in time, the electrons will move together because they sense each other. They're close enough that the electrons in this one are now on this side, and this has the partial negative. And the same thing happens on the neighboring molecule. And so you get an alignment of the dipoles, but they're in the opposite direction. And it's this continuous fluctuation. Your PowerPoint slides show that. Let me see if I can find it.
Wait a minute.
Uh-huh.
No, the wife just came in.
Oh. Let me see. This is the PowerPoint. It's really hard to imagine it, but there is a slide that shows it. Oh, where'd it go? This is it here. A little bit. Maybe. Let me keep going, I think. This is it here. So these are helium atoms, and they're showing the two electrons when you have them non-interacting, right? The electrons move in whatever random way they do. But when they're close enough together, you get a synchronization in how they move. And they move in a way where this atom feels the motions of the electrons. There's no full partial, there's no full charge like in the ion pair. There's no partial charge that's permanent. I just got to notice. How's the audio?
It's good now.
Okay. There's no full charge. That's the ion pair, that's the strongest. There's no permanent dipoles. The dipole-dipole interactions are sort of the next strongest. These are just these weak, small, temporary dipoles. Those are the weakest. Okay. One thing that's worth understanding is that the bigger the radius, the more you can polarize the electrons. So dispersion forces in xenon, which has a bigger molar mass than helium, are going to be stronger than dispersion forces in helium. And it's reflected in the boiling point. The boiling point of helium is 4.2 Kelvin, and the boiling point of xenon is 165 Kelvin. And that's just because it's bigger and the electrons in the outer clouds are more weakly held. Okay, now this is a plot of the boiling points of hydrocarbons, right? C5H12, C6H14. There are only carbons and hydrogens here. If you see a molecule that has only carbons and hydrogens, it can only have dispersion forces. But notice, the longer the chain, the higher the boiling point. So pentane has 5 carbons and its boiling point is about 35, that looks like. Nonane has 9 carbons and its boiling point is about 150. So, and that's because the molecules have more surface area to interact. And so there's more there's more dispersion forces between two molecules when they're bigger and there's more surface area. If you get to take, well, you guys aren't headed in that track. The 100 students take 130 and we learn about that in 130. If you go on to organic chemistry, you'll learn a lot more about this. But the bigger the hydrocarbon, the more the dispersion forces, the higher the boiling point. I'm not going to worry about this so much.
Looks good.
I know I'm hungry. Is it lunchtime yet? No.
That's it.
Okay, so this is the dipole-dipole interactions that I was mentioning before. And what I don't like about this slide is just that it hides a little bit for you what the molecules are. This is actually I'm gonna put my thing flat so I can write on this more easily. This molecule is CH3, right? So this is dipole-dipole interactions, and this is two of that same molecule, and here is where the dipole is, and it's showing them lined up. And so a good question you might get asked is, which of these molecules do you expect to have a higher boiling point? Here's formaldehyde. It can have a dipole-dipole interaction because of the dipole on that carbonyl, the C double bond O. Ethane is the same molar mass, but it can only have van der Waals interactions. So I might give you these two molecules and ask you what kind of IMFs can they have? And the answer is, for formaldehyde, you would say dipole-dipole interaction and dispersion forces. For ethane, you could say only dispersion forces because there's no polarity bonds. And then another question would be, which one will have a higher boiling point? And it's going to be the one that has the dipole-dipole interaction. And so this slide here is showing you 4 different molecules with different levels of polarity. And it's showing that, so here's the polarity is indicated by the dipole size. Propane has only 0.08 dpi. This is acetonitrile, and it has 3.92 dpi, and it has the higher boiling point. Again, the attractive forces. This would be dispersion. This is going to be dipole-dipole. Okay.
So can you go back to that one other screen?
Yeah, hold on. I'm going to put my keyboard back on. Oops. Let me see. This one here?
Yeah. So that bottom one, that would be dipole and dispersion, correct?
Yes, the bottom one?
Right.
Yeah.
Okay.
But if I'm asking you which kind, if I'm asking for one kind of force, you would say dipole-dipole. But any molecule that has, I mean, this is actually showing you the interaction between two dipoles. So this is exhibiting a dipole-dipole interaction. But a molecule that would have the dipole-dipole would also have the dispersion force. Okay, so if you're given something like this, choose a substance with in each pair with the highest boiling point. This is a hydrocarbon with 2 fluorines, so it has 2 polar bonds. And this is a hydrocarbon with 2 fluorines on 1 carbon. The fact that these two fluorines are on the same carbon is going to make a higher dipole, so this is going to have the higher boiling point.
Can you explain why that has a higher dipole one more time?
Because you have a partial negative on each fluorine, right?
Right, right.
And because they're both pulling away from the same carbon, it's
Yes.
gonna be more polar.
Okay, and that's why it has a higher dipole.
Yeah, and then remember, higher dipole, higher boiling point.
Yes.
Okay, now on this, our carbon bonds don't rotate. They're fixed in place. So this hydrogen is here and this chlorine is here and there's no rotation. So we have the same molecular formula, but in this case, the dipoles go like this and like this. On this molecule, they go like that and they go like that. These subtract from each other, these add. So this is going to have the higher boiling point. So, and the same things that contribute to higher boiling points, also, it's the same kind of logic to look at solubility. Remember, oil and water don't mix. Polar molecules dissolve polar solvent, or are dissolved by polar solvents. So ethanol and water mix in all proportions, right? We can have, what is it? Absolute alcohol is, what's the percentage on that? It's really high. I don't know. When two liquids completely mix, we call them miscible, and alcohol and water are miscible. Polar solvents. Non-polar solvents look like this. This is hexane, toluene, and carbon tetrachloride. So they are going to tend to dissolve non-polar molecules. And then hydrogen bonding. The H's have to be attached to an F, oops, or an O or an N, but not a C. So all those hydrocarbons cannot hydrogen bond. And this is showing the hydrogen bonding in hydrofluoric acid. So the hydrogen bonding is just like a dipole-dipole interaction. It's just that it involves a hydrogen bonded to an N or an O or an F, but not a C. Okay. So look at this example here. And again, what I don't love is that it doesn't show you the molecules. So let me draw them. Let me copy this. Okay, so here's ethanol. Actually, I'm going to put this in the middle. Oh, go away. Okay. Okay, so ethanol is this molecule. Carbon attached to 3 H's, another carbon-carbon bond, and an OH group. This is dimethyl ether. Okay, so there's one hydrogen and one oxygen in ethanol that can hydrogen bond. This hydrogen can hydrogen bond to oxygens on another ethanol. It would look like this. Right, so here's my hydrogen bond. Notice that,
Are you on your whiteboard now, Professor?
oh, no, I'm on the, do you not see it?
No, I don't see it. I just see the screen for the hydrogen bonding, the slide.
It's showing me the slide that I'm sharing it. How about now? Do you see it now? What do you see?
I see the bottom where you wrote the C, the O, and H, that
Okay,
configuration.
the dimethyl ether. And do you see the red circle up here?
Yes.
Yeah.
Okay, and the hydrogen bond. Okay, so couple things. So ethanol and any alcohol, ethanol, methanol, those can all hydrogen bond. Ether, notice down here, there's no hydrogen that can hydrogen bond, right? Let me change colors up here. I'm gonna put a green circle around all the hydrogens that cannot hydrogen bond in ethanol, right? Those are all attached to carbon. They cannot participate in hydrogen bonds. If we look down here at dimethyl ether, all of the hydrogens are attached to carbons, so none of them can participate in a hydrogen bond. Because there's no hydrogen bonding, the boiling point is lower than the boiling point of ethanol. It's minus 22 degrees Celsius. Ethanol has a boiling point of 78, positive 78 Celsius. And they have the same molecular formula. It's just because the intermolecular forces that they each have. Dimethyl ether is going to have dispersion and dipole-dipole, but the dipoles aren't very strong. Ethanol has dispersion, dipole-dipole, but most importantly, hydrogen bonding increases the boiling point. When you get into the homework, I think it will be helpful. Let me see what else I have. This is the slide. They, for some reason, I think this is the only book I've ever taught in where they arrange the intermolecular forces from weakest to strongest. And so my brain, after 33 decades of teaching, can't flip it. So I always do the strongest first. But it's showing you the same thing that I drew on the whiteboard here. But it doesn't show you the chemical formulas. But at this point, you can figure it out, right? This is water, and that's a cation. This is water, that's acetone again, or formaldehyde. Sorry. Okay. So I think at this point, spend some time with it. I think you will feel better when you do the homework questions. And again, the exam is going to have stuff very similar to the homework. If you're finding that there's something that's tricky, let me know. Oh, do you want to look at this? This is actually here. Practice, pick the compound in each pair expected to have higher solubility in water. This one has an oxygen on the left, and this one is just a hydrocarbon. This is going to make it more soluble. This one has an NH, and this is just a hydrocarbon, so this will be more soluble. Now we have ethanol, and we have 1, 2, 3, 4. This is pentanol. It's got a much more non-polar part, and that part's polar. This has non-polar part, the ethanol, but it's small relative to the polar part. So ethanol is going to be more soluble. Those are the kinds of questions that you'll find on the homework, and it'll all be similar to what I put on the exam. Do you guys have any questions now? Uh-oh, it's telling me my audio is not good.
You're still there.
I'm still here.
Yeah,
Okay. Sometimes I sacrifice the chat window so I have more real estate on the screen because I'm just doing this on my little surface. But then if something goes wrong, you guys have no way of telling me. Okay, so I think I'm gonna stop there. Let me know how much you guys want a Zoom on Wednesday. Um, and ask questions between now and then. Okay?
So if we have a question between now and Wednesday, should we email you then?
Yeah, please.
Okay.
And I'll try to sit down and either do a video or write something out, or it'll tell me that we really do need to meet Wednesday if there's lots of them.
Okay.
Okay. Great. I think I'm gonna end there. If there's no more questions, probably at this point you just need to sit down and look at it and work the homework.
All right. Well, thank you for answering my questions.
Oh, I'm always happy to get questions to have to do for the class because it usually it gives me something to focus on when we start. And also if one person's struggling with it, chances are others are too.
Right.
Okay, take care, guys.
Thank you.
Bye.
Thank you.
Professor. Thank you.
Bye.